Thanks everyone for making it for the meetup. It's great to see some familiar faces and some new ones. Today we have like two very interesting speakers for you. First up is Senthil. Senthil is a senior engineer at Snowflake. He has had nearly 2 decades of experience working on various storage technologies. He's been awarded like multiple patents. At Snowflake, he's one of the key features that he worked on was the snapshot-based backup and restore. And he's also responsible for designing the control plane subsystem for managing fleets of FoundationDB clusters. So today he's going to give us some insights into how that control plane has been designed and some sort of taste of how FTB is used at Snowflake. So without further ado, help me welcome Senthil to the stage.
Hi everyone, my name is Senthil, as Arvind introduced me. I work in the FoundationDB team at Snowflake. I started off, designing this snapshot-based backup for FoundationDB and worked on the core KV software for like a year and a half. And then I started working on the control plane, the architecture design from day one. This is a vast area, FDB control plane is a vast area, but we will kind of touch upon the overview, architecture, and few concepts, a few contexts here. And in a future talk, maybe we'll drill down into some specific areas. I just came back from India like 2 days back. I'm super jet lagged, and if I'm slow, bear with me. This is the agenda. I'll give a quick introduction for FoundationDB itself, the KV store, and then we will talk a little bit about FoundationDB at Snowflake, like the scale and how we use it, why you use it, how we use it, etc. And we'll talk a little bit generic kind of introduction of control plane itself, and what control plane means, etc. And then we will look at the control plane for FDB and overall architecture, and then look at some workflows that we use often. And I think that will be used for anybody who is using FoundationDB needs those workflows. We'll look at some details of that, and we'll talk about some principles and lessons that we have been using that worked and some issues that we run into. And we'll give some time for Q&A. So FoundationDB is a distributed key value store. It's highly scalable, fault tolerant, and asset compliant, and pretty reliable system. It's highly scalable that you can add nodes to get capacity and performance. There are some scaling limits, but it's pretty much it scales pretty well to some to the capacity. It has all the asset properties, and it has strict serialization capabilities. So the consistency is pretty good for application development, that you don't need to deal with any issues that come out of non-asset-based databases. And also it's fault tolerant. It has good capabilities if there are failed machines, etc. It has capabilities to re-replicate the data to other nodes and reroute the reads and writes. Are some of the features that are available there. And the other interesting thing about FoundationDB is the deterministic simulation testing, which is essentially is a framework where you can simulate many database scenarios with all kinds of failures, network disk failures, and all kinds of race conditions and test the software. So the simulation testing kind of gives you high confidence on the maturity of the software itself. So instead of running a software many years and get the maturity what it is required, the deterministic simulation testing framework lets you run this tests many times, like hundreds of thousands and millions of times, and test on various race conditions, and you can validate and improve the maturity of the software. And also, it's the more about the deterministic simulation testing is that you can not only reproduce some failure conditions, and you can deterministically replay it, which is great for debugging all the issues that you run into. So overall, it's a pretty good system for like running a complex application on a distributed system, which is scalable and also reliable and has mainly consistency guarantees that helps applications be written without worrying about consistency issues. Also, it has the multi-model approach where like the core KV provides the key value mapping thing, and then you can build on top of it things like either a graph database or a SQL database, etc. So that is also, it has a layered approach. So that's like kind of the summary of FoundationDB. It's a distributed KV store with scalable, reliable, and complete ACID compliance. FoundationDB at Snowflake. So what does it power? So we use FoundationDB mainly to store the metadata of a number of critical services within Snowflake. The majority of the metadata is stored in Snowflake. And just as some simple concrete examples are like all the customer data, all the accounts, the list of warehouses, users, all that is stored in the FoundationDB database. Why FoundationDB? It's the first thing is the correctness, the thing that we talked about, the maturity of the software with the deterministic simulation testing gives a lot of confidence to host your key critical data on FoundationDB. And strong consistency and serializability is another thing that ensures that at application level, you're not dealing with non-ACID issues that arise. It also has multi-row atomic updates. The benefits are you don't need to deal with half-updated states, or if multiple people are updating the concurrency updates, or any data integrity issues. So most of our clusters, all of our clusters are run on the cloud. We are multi-cloud. We run our clusters on AWS, GCP, and Azure. We use a combination of EBS and local disks for our clusters. And we use a redundancy mode called 3 data hall. In short, it is like you can think of it as, we keep 3 copies of the data, but it's a little bit more nuanced. But I won't go into the details here. We have a number of clusters. Some of the smaller clusters, we have tens of machines and few hundreds of processes. The larger clusters have hundreds of machines and can go up to 500 plus processes. And the workload varies depending on the size of the clusters. And overall, we have hundreds of clusters and thousands of machines across many regions and clouds. So talking of control plane, control plane is a system that is responsible for deploying the clusters, managing them, controlling all the operations, orchestrating all the operations, the configuration and the behavior of the system. And that's a pretty broad definition. The one way I try to look at it is that it should basically, control plane should provide the ability for you to manage the cluster with a lot of ease. And it should have all the components necessary to build a fully managed service. So that's how we look at it. And the other way to look at the control plane is that anything that is not a data plane is control plane. So if you take it FoundationDB, if you ignore the core read-write path, everything else associated with running that service, be it data distribution, replication, or you know deployment, rollouts, all this can be clubbed as control plane of the system. FDB itself, the core FDB KV software itself provides a number of control plane features. It provides cluster coordination, which is the leader election, the zookeeper equivalent, the node failure resilience, where if a machine fails, it's able to re-replicate the data and rewrite the reads and writes. All that is provided by the core KV software itself, and it does the read-write routing and also the role recruitment. So in FoundationDB, like each machine will typically run multiple FoundationDB process, and each of them will have a class or capability, what it can run, and the FoundationDB cluster at runtime decide what role it will play. So the class is basically the capability of it, and the role decides what runtime it will, what capabilities it run. All that is kind of packed inside the KV software itself. The rest of the stuff that we're talking about in terms of deployment, configuration management, automation of cluster operation, monitoring, all that is done on top of it, outside the core KV. This is a simple picture that kind of explains that anything that is outside the FDB cluster that provides the control plane features. Everything else has to be done outside of the KV software in the FDB control plane, and which is pretty broad. Some of the things that I've listed is provisioning, which is bringing up the cluster, configuration of the cluster, changing the configuration of the clusters, automation of the common operations. They'll detail what those operations are in a bit. And things like auto healing, auto scaling, and monitoring and alerting, all the stuff has to be done outside of the core KV, and broadly we call it control plane. And concretely, to think about like how does the architecture of a control plane looks like. So I'm not specifically talking about any particular technology in terms of Kubernetes or like Terraform versus some Chef or something like that, just generic control plane components. There is a persistence layer that is necessary for any of the control plane to maintain the metadata of all the infrastructure being maintained. Here, like in the FDB cluster context, it could be the machines that are part of the cluster, the list of the clusters themselves, all the parameters that you have set on the cluster, all that, all the operations that the user wants to do, all that is kind of fits in the area of the persistence, will be stored in some persistence layer. You need that. And then you have a compute layer to orchestrate the workflow and monitoring, like all the business logic associated with that is kind of fits in the compute layer bucket. And to manipulate the cluster, you need some client or API or REST endpoint to which you can talk to the cluster. In FoundationDB case, there is, I'll talk about what is available with FoundationDB. And you may need to do some operations on the host other than the cluster. You may need to manipulate the cluster sometimes, and sometimes you need to manipulate the host itself, like you want to write a file or like modify something in on the host level. So you need some agent on each of the machines that you're managing, and you can you run on it, and you can compare this to any of the architecture, Kubernetes. All of this will have something similar. So this is the picture, like you have a persistence layer where you store the state and of the infrastructure replication, and you have a bunch of a set of FDB machines, each having an agent. And the orchestrator or the monitor talks to these clusters. To manipulate the cluster, we use FDB CLI, which is a binary that can talk to the cluster to do some operations. You can for example, change the redundancy mode of the system, or like add a node or delete a node. All that is possible by FDB CLI commands that you can issue to the cluster. And then you have agent commands. If you want to download a binary or like change a file or something like that, then you can use the agent. So that's like the broad architecture of the control plane. So the two components that I want to introduce that will be useful, and for folks who are already working on FoundationDB, this may be familiar. There's this thing called FDB cluster file. You can think of that as a connection string, and that string is available on each FDB server and each FDB client. And that is how the machines can talk to each other. And it is comprised of cluster name. There's a magic and a list of machines that make the coordinator state or the zookeeper state of that. So this is kind of necessary at the runtime to, if you're bringing in a new mission, it should know this connection string to be accessible and available. And there's the conf file. This file details all the processes that are running on the machine. This both cluster file and conf file is per machine, and conf file has the list of processes that are running it. It has network configuration where the cluster file is present, and details about the disk and all the parameters that are going to be run with. And memory settings and all those stuff are stored in the FoundationDB.conf file. It's just a .ini file. And has all the settings that are necessary to bring up the FoundationDB services on our system. Now we will kind of a little bit go into like some of the features or some of the workflows and look at the details of that. So the most common is you need to bring up the clusters or you need to deploy the clusters. And some of the frequently run operations from our side, it would be common in anybody who runs a managed service or FoundationDB is you need to upgrade these clusters frequently if you want the newer features. And hardware upgrade, which is to replace the hardware. And the knobs or parameters are basically parameters to the FoundationDB cluster. And if you want to change that, that's a common operation we do, backup and restore. And then we talk about auto healing and auto scaling. And then configuration management, which is like broadly, ability to, keep the configuration of all the clusters in a central repository like a GitHub and able to make a change to the GitHub and be able to deploy this change across the fleet is what I kind of broadly call this configuration management. And then monitoring, alerting, it's is what is necessary for many systems. So cluster bring up, we to bring up a cluster, you need a set of specifications provided by the operator. In FDB case, you need the list of machines and the topology, like which failure domains, where the machines are going to be placed. All the parameters associated with each of the machine and each of the process type, you need to be specified. OS image, redundancy mode, and cluster name, and set of other parameters. Broadly, the workflow will look like you provision the machines that are asked for and set up those machines with the user specification, and then you configure the database and validate it as operational. And the setup itself is a little more involved in the sense that you are setting up the disks, the mount points, and the file system. And the thing that I talked about, the FTP or the cluster file and the conf file based on the cluster specification provided, and you configure the database, which is to create the database. You can also leverage the machine image, so you can bake in a bunch of stuff in the machine image versus do it as a post setup after provisioning. If you do those setup before the machine image, then it is kind of relevant. It'll improve your kind of the setup time. The other most common operation that will be necessary is software upgrade, and we do hundreds of upgrades every month when there is a new patch release or any release. Um, and here, one of the interesting things to note is that typical distributed systems, we upgrade, something called a rolling upgrade, right? You upgrade one machine and then go to the next machine and then go to the next. In FDB, there's this thing called the insta upgrade, where all the machines go from one version to the next version instantaneously. And if you're curious, many people run into this question, okay, why the insta upgrade is done? It kind of goes back to one of the important paradigm of FDB, which is they want everything to be tested with the simulation testing. And it's hard to do the simulation testing. So the simulation testing is testing all the scenarios and increasing the maturity of the software. If we have to do the rolling upgrades, then you need the simulation testing to be able to run two versions of the software, the old version and the new version that you're going to upgrade, and in different pieces, right? So that's a very hard thing to achieve. So it's that, you truly believe in this, deterministic simulation testing, and you take it to the extent that upgrades also needs to be tested for that short duration. And if it is not, you basically, you're not getting that maturity what is necessary for the software, and then that leads to doing this insta upgrade thing. So the overview of the workflow is like for, just for safety before the backup, we do the, backup the cluster before we do the upgrade. But after that, we just download the desired version of the software into each of these machines, and then, have a symlinks to point to the new binaries, and then we restart the machines on all the machines to point to the new version. This will cause a cluster recovery, and recoveries are part and parcel of the FTP cluster operation, and this will come up in the new version. It's typically the upgrades are very stable and successful. Very rarely it goes south, and in that case, you can always do a downgrade. The other operation that we can talk about is that we do commonly is the replace the fleet of machines as something called hardware upgrade. Here, the workflows, there is you basically provision a new set of machines that you want to add to the cluster with the new machine type, and you do a process called exclude, which is essentially evacuate all the data associated with the cluster and the roles that were on the old machine, and eventually terminate those machines, and then the new machines will form the cluster. This there is one kind of nuance in this thing, is that there are types of, you can exclude in the units of single machine. Like, if you have 100 machines, you do provision a new machine, exclude the old one, and then provision a new machine and exclude the old machine. You can go on like that. This will increase the amount of data that is transferred, because every new machine, then you're replicating out all the data that was present in that to get back to higher to get to the redundancy mode back to the normal. The other option is you can, exclude only machines that are in a particular failure domain. In our case, we exclude things that are within one availability zone in cloud environment. Or you can go ahead and do the entire cluster, which the entire cluster is the most optimal in terms of the amount of data transfer, because when you have the entire new machines provisioned and you do the exclude, the amount of data transferred is much minimal than like doing either the machine level exclude or trying to exclude it by by the failure zone, availability zone. The knobs and parameters in FoundationDB, all the knobs and parameters are just maintained in the ini file in the foundationdb.conf. So this means every time you need to change the parameter, it will involve rewriting this conf file and restarting the services. So that, yeah, that means you need to make sure that the file is like integrity is there. Otherwise, you need to backup, etc. Yeah, this is relatively straightforward. You are generating the new conf file, compute the new conf file, and restart the service, and that will ensure that the parameters are in effect. It's all the parameters are essentially command line arguments to the FTP server binary. I've linked a bunch of a set of examples of the parameters. The parameters range from all the way from what is the format of the log file, JSON versus XML, to the cache memory, to location of the cluster file. All that are simple key values elements inside the conf file. In terms of our planned improvements, the one thing that we are already have partially and like investing more is the auto healing and auto scaling capabilities. The auto healing is like a generic framework for us to monitor a certain condition and take an action on that. And the most common auto healing is essentially monitor for failed machines and replace the machines. FDB can handle the machine failure and try to move data out of the failed machine, but eventually that machine has to be removed out of the fleet and a new machine has to be provisioned. That's the auto healing part of it. Auto scaling again is like a generic framework for monitoring some resource, either it's a disk usage or like CPU utilization of the storage servers, and they scale the clusters up and down based on based on the usage. This basically these two gives the ability to do zero-touch management, that you don't need to manipulate the cluster by an operator, and the cluster is kind of self-managed, and you need less operator intervention to deal with these machines. And the other is the configuration management, which is kind of a centralized repo for all the configuration, and these configurations are version controlled. And we have the ability to identify the machines the clusters that are diverging the configuration, and the ability to roll out this configuration in a safe fashion across the fleet is other thing that we are investing in. Some of the principles and lessons learned I would go is the first is the correctness is super critical for managing stateful systems. Any mistake here will lead to a data loss, and I think of it as the control plane as the keys to the kingdom. It's more powerful than the data plane in many areas. So if there is a mistake, you can lose data. To that extent, we do a set of things. For example, we serialize the operations that we do on the cluster. Like we don't do like as much as possible a software upgrade and a hardware upgrade, or a knob change and a software upgrade simultaneously. We just serialize them. And also for the stateful systems, latency associated with adding a node or deleting a node is not super critical. If instead of, let's say, it takes 30 seconds to provision a brand new machine, or if it takes 1 minute, it's not super important, because eventually you have to move the data out and in of the inside the machine, which takes much larger time. So correctness is like by far more important, and given the damage it can be caused by one small issue, the investment for correctness should be super critical here. And the other thing is like, stopgap, like building the control plane, you will have, certain operations that are automated and managed, and some operations will be left as manual. In those cases, if there is a trade-off, it's better to go and do a suboptimal thing of getting rid of the machine, or do something that instead of trying to do a manual operation. Even a stopgap manual operation can, cause issues, because humans can cause mistakes, and that can have consequences. The other thing is for the control plane, there may be things where it runs into it's fully automated, but it runs into undefined situations. And in those cases, you have a choice whether it can make some assumptions and try to move forward, or stop and ask for the operator's help. But definitely for the stateful systems, it's better to do the former, to do the later, which is like not make any assumptions and ask for the operator to intervene. We follow in many cases, we follow this. For example, when we upgrade a cluster, we don't upgrade a cluster if the cluster is not healthy. Or when we or the other situation is when cluster is modified externally, like somebody else is adding a node or like getting rid of a machine or change the topology, then the control plane, we verify that the state of the system is same as the state of the system that we are trying to manage. And if it's different, then there is some external modification, and we try to back off and say that ask the operator to fix or override. And the last one is immutable infrastructure. So we try to avoid doing in place any updates as much as possible. We do no in place image upgrade. Most tooling we don't want to upgrade in place, and we just do the hardware upgrade as the mechanism to get to the new images or new tools. And one exception is the software upgrade, because that happens more commonly, and then we don't want to do that because the hardware upgrade means data movement, and that's like cost and latency, so we try to avoid that. But in general, it's great to have immutable infrastructure that takes away a number of things that you need to worry about. So yeah, this is the agenda that we talked about. We looked at the FoundationDB overview and some context of how FoundationDB to use it, Snowflake, and some general concepts of control plane, and some control plane features and workflows inside the control plane for FTB, and some future enhancements and some lessons learned. So I have some appendix slides, but if you have some questions and if I have to refer that, I'll use that. But otherwise, I'll leave some time for questions. Oh, okay.
So you mentioned about like you manage the FoundationDB, the control plane, and behind that there is a cluster. And may I know that how is your company or how Snowflake differentiates your other infrastructure with this kind of infrastructure? Normally, like for other companies, they may like have a whole infrastructure management team that manage all of the infrastructure that may run on Kubernetes or running on the bare metal machine. But for FoundationDB, it seems like you manage a different infrastructure with other service. So is there any difficulty that you have met to manage this kind of service? Also, what's the purpose of using this control plane to manage one isolated or one identical infrastructure other than other service or application?
Are you asking? I do not clearly understand the question. Can you
Yeah, it's pretty complicated. So in short, it will be like, what's the purpose? So is there any difficulty that running a whole different infrastructure than any other application by hosting or owning this service on your team? Like normally for other companies, they may have a same infrastructure for all of their application and they're running the Kubernetes or other bare metal. But it seems like for your team, they're running FoundationDB, you have a identical infrastructure on your own like that.
I see. Yeah. So we don't use Kubernetes because Kubernetes was not that matured when we started. And we kind of, FoundationDB uses, like we have other type of compute infrastructure in Snowflake. We kind of follow the similar model and have a custom engine that is built inside Snowflake and did not follow the Kubernetes model. But the concepts that I talked for the control plane will be very similar, whether you use Kubernetes or you build your custom engine.
I see. So may I ask, is there another layer of scheduler running behind to orchestrate a control plane of FoundationDB and other Snowflake infrastructure, or you manage on your own side?
Yeah, it's a custom engine for for FoundationDB. I can say that, yeah.
I see. Thank you.
So you spoke about instantaneous upgrades. Is the software upgrade instantaneous as well? And if yes, if there are any data structural changes or changes in, say, the metadata, how is that handled instantaneously?
Yeah, so the software upgrade is what I was saying as the insta upgrade. Like you have two choices, whether you do a rolling upgrade, which most systems, and FoundationDB does the insta upgrade, which I was talking about was the software upgrade. So if you look at the insta upgrade, it's nothing but a restart of the process, right? So your software, this is a case where you're just like, let's say the cluster is running at version X and you restart all the processes, right? It restarts in the version X, right? In the insta upgrade case, it goes from version X to version Y, right? Now, so in a normal operation, there is no difference. It's a version X to version Y, it continues. But if there are like on disk changes that if X and Y are not compatible, then there could be issues. There are in certain FDB versions in the past, it has to go through a specific sequence of software versions for it to be stable, and that has to be enforced externally. Right. So that caveat exists. I think that caveat will exist with anything, like even if you do a rolling upgrade and if you want the disk format to go through a certain version change, your B3 or whatever is the on disk has to go through certain version changes, then you need to enforce that. So that's kind of enforced externally here also. But insta upgrade itself has no kind of specifically doesn't have an impact directly on this.
Okay. And do you usually face any downtime, like for example, with version upgrades?
Yeah, in some test environments we do, but no, yeah, yeah.
Thank you.
I may have a follow-up question. Do you use any CMDB for managing your configuration items of all of this database?
CMDB?
Yeah, do you use CMDB or other concept or similar tool to manage your infrastructure running the control plane of FoundationDB?
No, not for FoundationDB. No, I don't use any of the CMDB.
Yeah, so in that case, is there any central configuration or any other way to monitor the configuration drift or infrastructure drift? Is there any tool or application that you use or build for this feature?
Yeah, that's an internal system that we use. That is, I don't know how much I can reveal that to you, but like it's an internal system. It is not, I don't think it's CMDB based.
I see. Thank you.
Okay, so my question is relating to the size of the cluster, right? So there is a recommendation around using not more than 500 processes per cluster. Do you run into that limit? Do you operate clusters that are larger than 500 processes? And the second question is, when you do the upgrade where you bring up an equivalent number of machines to minimize the data movement, potentially you can, if you have a cluster with 500 processes, you can go up to 1,000 processes. Do you run into this issue, and what is your experience running this in Snowflake?
Yeah, there is the scaling limit, and I specifically don't know exactly what the number is. There's a performance team that deals with it, but what I've noticed is I think we go up to like 600 or 700 process without issues. But we do, when we do the hardware upgrade for the largest clusters, we don't do the policy of replace all the machines at one go. We try to do it easy by availability zone. That's one precaution that we take. It could be originating from the scaling limits.
Okay, so that would limit it to a 30% increase at any given time,
Exactly,
rather than
yeah.
100% increase. Okay, so if there are no more questions, I think we can thank Senthil for an insightful talk. Thank you, Senthil.